All right, now let's talk about what isotopes are, especially in relation to ecology. I don't know why I stress the E so much. All right, so back to, let me get my slides moving. Back to your high school chemistry classes. So an element in the periodic table is defined by the number of protons in the atom nucleus. So for example, carbon has 6 protons, nitrogen has 7 protons, oxygen has 8 protons. So that's what really defines and differentiates different elements. So number of protons. Remember that the atomic mass is the sum of protons and neutrons. So for carbon, for example, this is actually carbon 12, you've got 6 protons and 6 neutrons. An isotope of an element is something that has the same protons, because remember that's what defines an element, but it has a different number of neutrons. So for example, carbon 12, which is the most common carbon we have in the atmosphere, has 6 neutrons. And then of course, if we look at the previous example, it has 6 protons. But carbon 13 has 7 neutrons, but of course still 6 protons. So it has an atomic mass of 13. So this is what's important about isotopes, is that they have a slightly different mass, but they function the same way for the most part. I mean, it's still a carbon. And so we'll talk about some of those slightly different functional attributes, but from a plant's perspective, it can still use carbon-13 in creating sugars and in photosynthesis, just like it can use in a carbon-12. But some of these small differences between them are important for understanding some ecological processes. So in ecology, some of the different ways they're used. So isotopes can integrate ecological processes in space and time. And so this is, we're going to use an example that fits into this. So we're looking at the integration of water use efficiency over time. Isotopes can indicate the presence and magnitude of key ecological processes. They record biological responses to earth-changing conditions. So I mentioned in the previous video that basically, I think I said it this way, that like tree rings, I don't think I said it this way, but tree rings like each year can record the water use efficiency of plants in that year. And so then that's stored over time. Yeah, we'll leave it at that. And then isotopes can trace the origin and movement of key elements and substances. And this can do this, one of the common ways you'll see it is that people will do tracer studies. So they'll actually introduce an isotope into a system and look at where it goes within that system. So I think some of this stuff will become more clear as we kind of go through some examples and talk about how we use carbon isotopes to measure water use efficiency. Okay, so what effect do the neutrons have? So remember, we've got, we're going to focus on carbon. So we've got carbon 12 and carbon 13. They've got the same number of protons, but carbon 13 has an extra neutron. So what's the impact of that extra neutron? So since neutrons have no charge, they're not going to change the chemical properties of an element. But because it has a heavier mass, that will impact some of the mainly it impacts rates of movement and rates of reactions. So the heavier isotope moves slower because it's got more mass, and the atomic attraction is greater, leading to stronger chemical bonds. Yeah, so we'll leave it at that for now. Just some things to think about what makes a good stable isotope. And I guess I should have one more slide about stable and non-stable isotopes. But, we've all heard of, radioactive carbon, or C14. So C14 is not stable. So it's breaking down over time because there's too many neutrons relative to the protons for it to be stable. And so then it gives off radiation as that carbon atom breaks down. But carbon 13 it's close enough in balance that it's stable and it's not going to break down over time. A C13 molecule today is going to be a C13 molecule or atom like in 1,000 years, whereas that's not the case with C14. So, yeah, so that's stable versus unstable. So what makes a good stable isotope for us to actually be able to use in ecology? Well, a big difference in mass between the two atoms is really helpful. So, for example, here is listed 3 different stable isotopes. The first one is deuterium divided by or in ratio to hydrogen. So hydrogen's stable isotope is deuterium, which weighs twice as much. So that's a huge mass difference. And so the differences in reactions between deuterium and hydrogen are really large. And so that's a useful isotope because we can easily pick up differences. The difference in mass between carbon-13 and carbon-12 is about 8%. So that's pretty good still, but not as great as deuterium. And then oxygen has a stable isotope as well with it. The main one, it actually has 2 stable isotopes, oxygen 17 and oxygen 18. But oxygen 18 is more common. And so the mass difference between those is 12%. And so these are all isotopes we use in ecology. And they have big enough mass differences that we can use them well to track responses and changes in the relative abundance of each isotope. Having a low atomic mass is pretty good because then they tend to react more naturally in biological processes. I'm going to jump down. The second one's not super important for us. So forms compounds with a high variety of bonding neighbors. That's mainly like that it responds like it's, well, this is more like, okay, if you have an isotope that doesn't react with anything, that's not really helpful, right? So you need an isotope or an element that reacts with lots of different things so we can actually see where it's moving throughout the plant. And then the last one is the rare isotope is a small fraction of the total. And that just helps us identify differences in the ratio of C13 to like C12, for example. So let me just say something here. I'm not going to talk a lot about how we measure these ratios between these two things, but we use a mass spectrometer, which that allows us to separate elements by their mass. And so we can detect, we can put a sample into a mass spectrometer and separate carbon-12 from carbon-13 and see how much there is of each one. I'm going to talk a lot about the ratios because it's really hard for us to measure the absolute concentration or absolute amount of C13. But what we can do is see how much C13 there is relative to C12. And so we're measuring the ratio of those two at the same time. And I just want to explain that because I'm probably going to talk about ratios a lot. And maybe that helps you understand why I'm using that term so much in this particular section. Okay, so I kind of mentioned this a little bit in how isotopes are used in ecology, but there's kind of 2 different types of studies and ways of using isotopes. The one is just looking at the variation in the natural abundance of C13 versus C12 in our example. So we can just look at what's naturally there. And how that naturally changes through biological processes. But then you can also use tracers. So for example, we could get CO2. So let's say we're growing a plant and we want to track something about photosynthesis. We could get a tank of CO2 that had almost all of the carbons were C13. And then we could expose the plant to that air for a little bit so that during photosynthesis it's using all C13. And then we would take away that tank of air and then we'd watch that C13 move through the plant. And so that would be considered a tracer study. They do this a lot more with nutrients. So there's a stable isotope for nitrogen, and so that you can add nitrogen with kind of like a spike in the heavier isotope. So the heavier isotope is always going to be the one with the highest number, right? Because it has more neutrons. So for nitrogen, there's the most common isotope is N14, but there's also N15. And so you can dump a bunch of nitrogen with N15 into like the soil, for example, and see what plants are using it at what rates. So that's an example of a tracer study, or two examples, I guess. Okay, so just a slide here just to see the differences in concentration between the light and the heavy isotope that naturally occurs. And then this lists basically the 4 most common isotopes we use in ecology. I think that would be fair to say. So the first one is hydrogen. So the most common isotope is hydrogen that has a mass of 1. And so you can see that makes up almost 100% of the hydrogen in the atmosphere. And then deuterium, which again is the heavier stable isotope, it has an extra neutron, it's making up much less than 1%. So there's a really big difference between the concentration of those two isotopes. But remember, the mass difference is also huge. So physical processes really can differentiate. Like these two atoms react at very different rates because of that big difference in mass. Carbon isotope, which is the one we're going to use. So carbon-12 is the most common atom of carbon, and it makes up almost 99% of what's in the atmosphere. And then carbon-13 makes up, of course, the rest, so just over 1%. So pretty big differences in concentration there. Nitrogen, which I just mentioned, the most common atom is N14, and then the heavier isotope is N15. So you can see pretty big differences in the concentration. And then oxygen is the other one. You can see the most common oxygen atom is the O16, which makes up, again, well over 99% of what's in the atmosphere. I mentioned there is a stable oxygen, or O17, but you can see how little of this stable isotope there is. And then O18 makes up about 2% of what's in the atmosphere. And so you can kind of see here, I talked about carbon a little bit, and we're going to talk more about it. I talked about nitrogen in a second. Then with the hydrogen and the oxygen, like we can do a lot with those in tracking kind of how plants are using water, where they're getting those their water from, and so that's how those two are used a lot in plant physiological studies. We won't talk about them in this particular example, but just so you know, that's a possibility. Okay, just one or two more things here. So this first bullet point talks about, basically kind of tells you how we're presenting the data for natural abundance isotopes. And this is again because of the way we measure stable isotopes. We measure them as an abundance. So we would measure the ratio, and we would report the abundance of the rare isotope. So if we're talking carbon, carbon-13 is the rare isotope, and you divide that by the abundance of the common isotope, which is carbon-12. So this is kind of what you get when you measure some tissue, or we'll keep it at tissue for now. So if you're going to take you can take a leaf, you can combust it. It breaks all of those, all of the elements in that tissue, into their individual components, and then you can figure out how much C12 there is and how much C13 there is. The way we report that is with this delta notation. So we're going to take, because it's really hard, so let's go back for just a second. So notice on a lot of these isotopes how very few how low of a concentration these rare isotopes are. 0.2%, 0.015%. For O17 it's 0.038%. So there's very few of these atoms, in the tissue and in the air. And so, as I mentioned before, it's really hard to measure the absolute amount of, for example, C13. So we measure it as the ratio, which I already said. But the other thing is, because it's so hard to measure, we measure it relative to a standard that we know the carbon-13 and carbon-12 of. And so, like, not every time, but like, for example, I ran an isotope lab for a while. And so when we were to measure samples and we were to estimate the ratio, every like 10 samples, we'd run a standard. And so you continually compare your sample to some standard to make sure you're getting accurate data. So the way we report our results are relative to that standard. So this is the isotope ratio of the sample divided by the isotope ratio of the standard. You subtract 1 from it and multiply it by 1,000. The details of like this calculation aren't super important for us, but what I want to just introduce you is the notation. So we're going to be reporting, or we're going to look at data reporting the isotope ratios in delta values is how we refer to them. This symbol here represents, it's almost like percent, but it's per 1,000. And that comes from the fact that we're multiplying it by 1,000. If we didn't do that, we would just be dealing with values of like 0.001 versus 0.002. So it really just like makes those numbers a little bit larger and maybe easier for our brains to process. So that's where the 1,000 comes from. But anyway, it's a delta notation to describe the isotope ratio of different tissues. Okay, let's talk briefly. So what causes variation in the isotopes? So why is it even useful for us in ecology? So we'll just talk about a few examples, and then we'll talk about it more in the next video. But for carbon, CO2 in the bulk atmosphere, the delta notation, for carbon, we're dealing with negative values. So bulk atmosphere, if you were to measure the ratio of C13 to C12, we would be in the -8 range. And that's -8 per mil. That's how you would read this symbol here. So it looks like a percent, it's got this extra 0 so it's per mil. CO2 in fossil fuel, and that comes from burning of biomass, is around -28 per mil. We won't talk about this in too great a detail, but this is one way we've been able to figure how much of the CO2 increase in the atmosphere comes from us, like, you know, extracting coal and petroleum from below ground and combusting it to get energy. We can track that through the isotopes. Oxygen and hydrogen, as I mentioned, they help us look at differences in sources of water. Groundwater tends to have a very different isotopic signature from precipitation, and so you can kind of look at what types of resources plants are utilizing to get their water. And there's two ways that the isotope ratio can change. And so there's, and we call these fractionation events. So fractionation is when something prefers one isotope over the other, it results in a change in that ratio, or fractionation. There's an equilibrium fractionation, which we're not going to talk about, and then there's a kinetic fractionation. Kinetic fractionation is like a physical process. So, for example, the first one is diffusion. So the heavy isotope is going to diffuse slower than the light isotope because it's got greater mass. So for example, if you've got CO2 with a carbon-13 atom in it versus a carbon-12, that heavy CO2, or the CO2 with the carbon-13 in it, is going to diffuse slower through a stomate. So you can maybe start to see like, oh yeah, we could use this to track how open a stomate is and how fast those different atoms of CO2 are getting into the leaf. They also have, the other one I'm going to focus on is enzymatic reactions. So some enzymes prefer one isotope versus the other. One of the main enzymes that cares about the isotope is ribisco. Ribisco reacts much faster with a CO2 molecule that has C12 in it than a CO2 molecule that has C13. So we can look at how much ribisco is in there and how it's how it's functioning based on how many CO2 molecules it's taking with C12 versus C13. Okay, I talked about isotopes integrating ecological processes in space and time, and so I just want to give you like a couple of examples. The one way that isotopes are used a lot in ecology is looking at trophic levels. And so there's a saying in isotopes that you are what you eat plus a fractionation factor. So we talked about fractionation being the change in the isotope ratio. So for example, if we were, going to look at the some trophic interactions. We've got a plant, we've got an insect, and then let's say we've got a fish eating that insect. So and we've got an isotope ratio of the plant. Let's say I'm just going to make up a number. Let's say it's 10. When the insect eats that plant, it's gonna be close to 10, but there's a fractionation factor, so it's going to change the isotope ratio a little bit. Let's say the insect then has an isotope ratio of 12. Well, then the fish is going to eat the insect and it's going to fractionate a little bit more. So maybe, let's say the value now is 14. And so you can look at how many levels there are in those trophic levels and what animals are eating what. And so it's been a powerful tool in looking at those different trophic interactions. Let's just leave it at there for a nice example. Isn't that a nice example? We also use it a lot for water, which is what we're going to talk about. And so the isotope values of C13 in particular, or the abundance of C13 changes a lot, whether a plant is stressed or relatively happy with regards to water. And then just one example of how you can use this. I mentioned this a couple times, but here's some data. So the tree rings record something about the environmental conditions in that particular year. And so this is, they reported it as like CICA, which we'll talk about in a second, but they got this data from carbon isotopes. And you can see, like, we get these different values in year to year between different plants. And you can, if you kind of look at these two lines, so the upper one's a pine, this is a fir, and then here's our precipitation down here, you can see those isotope ratios are following the patterns of precip to some degree. But then you can see parts of the curve, like in this area here, the pine isotope ratio is going in one direction while the fir is going in a slightly different direction. And so then we can really start to pick up how different species are responding to these different environmental conditions. So it's a useful tool to go back in time. Okay, so that's just a little bit about isotopes. There's lots of stuff I glossed over, so if you have questions, like, let's go ahead and talk about them, especially next Wednesday in class. We're going to do an isotope activity. If you want to know more about measurements or things like that, let me know. We can talk more about that. But for now, I'll pause, and then we'll talk more specifically about carbon isotope ratios.